Chapter 2, Atoms and Elements. So if you cut up a piece of graphite, like from the end of your pencil, and you cut it in half, and then you cut the half in half, and you cut the half of the half in half, and how far could you go? Could you keep cutting it infinitely? No, you couldn't. Because eventually, you're going to end up with individual carbon atoms. And this is an idea that took humans quite a long time to come up with. The Greek philosophers sat around and talked about and thought about stuff like this, but they didn't actually do experiments. But some of them felt like, no, you could just keep dividing it indefinitely. But actually, you cannot. You get down to a certain point, and you get to an atom. And the word atom comes from the Greek word atomos, meaning indivisible. So you cannot divide a carbon atom into smaller pieces and still have it be carbon. Can you destroy atoms? Yes, you can. But when you destroy or divide a carbon atom, it's not carbon anymore. It's going to be something else. And atoms compose all matter. So we have to understand atoms if we're going to try to understand matter, which is what we're here for in chemistry. In 1981, which probably sounds like ancient history to most of you guys, but really isn't that long ago, Binnig and Rohrer were working in their laboratory, and as scientists often do, they worked late into the night, and they developed something that's called scanning tunneling microscopy, or STM. This is a very, very fancy kind of a microscope, but it doesn't use visual. It's not that it's just magnifying things, but it's using electricity to image something extremely small. And it can image even individual atoms and molecules. So here's an illustration of how this works. So there's a tip on this microscope, and it is moved over the surface that it's examining. And it does this raster pattern, and it goes back and forth in very small movements. And it looks at, it keeps the distance here from the end of the tip to the surface a constant distance. And it does that because of this tunneling current. It passes an electric current from the tip of this through the air into the object that's being examined. They keep this current constant, and that allows them to, they can move the tip up and down, and by the movements of the tip, they can tell where there are little bumps or whatever on the surface. And this is one of those subjects that I want you to understand how this works and say, oh, wow, look, they can do that. I'm not going to quiz you on the principles behind scanning tunneling microscopy, okay? But this is a technique that allows us to visualize individual atoms. There's got to be, there's no picture? Come on. Good grief, I don't have a picture of an atom. That's really sad. It should be there.
What does it look like?
Well, the images from this end up looking kind of like cones. So here's a slide I pulled up from a different presentation. But this is an image of atoms achieved using a scanning tunneling microscope. And you can see that they look like they're little cones or something, and they actually are not. But as that probe moves over the surface and it goes up and down to keep the current constant, this is the best resolution that we can get. But here, these are the Japanese kanji characters for the word atom. And they made this using individual iron atoms on a copper surface. So this is the kind of, stuff that a chemist thinks is fun. I've also seen them spell out things like IBM and do your homework. It's like, ooh. Now, doing that, obviously, it takes a fair amount of effort and specialized equipment to make those letters out of atoms. But it makes for cool pictures to show students. So I need to put that in my other PowerPoint presentation.
So if you had that copper slate with that stuff written on it,
Mm-hmm.
you'd never be able to discern anything, right? It'd be
No, if you looked at this with these kanji characters written in individual iron atoms on the copper surface, you would not be able to tell at all that there was anything on there. And you couldn't feel it or anything because atoms are so unbelievably small. They're just mind-bogglingly small. Good question. So atoms, really, really small, but they're very important for connecting the macroscopic, meaning the things that we can see with our eyes, the world that we interact with the microscopic world, which is stuff you would have to look at with a microscope. The atom is the smallest identifiable unit of an element. There's about 91 naturally occurring elements. Depending on who you talk to, they might give you a slightly different number. Some books say 88. There's over 20 synthetic elements. How do you get a synthetic element? Well, those are man-made. And they make them in a lab, and they're very unstable, which is why they don't exist in nature, because they fall apart really, really quickly. On the periodic table, at the bottom here, you see Un-S, Un-O, Un-E. Those are synthetic elements that haven't been given official names yet, or their names have not made it to a periodic table that we actually own. They might have been named and the table's too old. And if we look at their atomic masses underneath, they're just in parentheses, that's an estimate. They're so unstable that you can't even get enough of them together to weigh them before they're just disintegrating. They're very radioactive and they fall apart all by themselves. So we don't worry about those too much.